Hi all. In our today's session, we will mainly start with a very important topic, mensuration three-dimensional figures, because we have already discussed various varieties of problems in mensuration two-dimensional figures. Today our concentration will be on today and our upcoming classes. In fact, we will concentrate more on mensuration three-dimensional figures, one of the very important topic if you are preparing for SSC examination. Close to around 8 to 10 questions will definitely comes in main paper. If you are preparing for SSC examination, close to 8 to 10 questions will come in this particular concept of mensuration three-dimensional figures. We will also see what are the varieties of questions that can be covered here, and we will see how we can tackle those questions in the most easiest format. Now, before we move on to our problems, first let us understand, or first let us map it out. What are the varieties of three-dimensional figures we are going to discuss in this particular topic, and how many questions approximately will be solving it, and then we will move on to problem solving so that our life becomes easy to relate whatever we have discussed right now to whatever the number of questions we have solved in the upcoming classes. Now, in this mensuration three-dimensional, let me record everything, let me put it on the screen, what all the things which we are going to discuss in this mensuration three-dimensional figures. First thing that we are going to discuss is on cube, which is something very important. First thing we are going to discuss is on cube. Next we are going to discuss is on cuboid, and then we will also see some of the very important questions in cylinders. Cylinders is what we are going to discuss. We will also see cone. These are the 4 C's of mensuration three-dimensional figures. 4 C's. First C is cube, second C is cuboid, third C is cylinder, fourth C is cone, and then we are going to discuss another very important concept on sphere. Another very important concept what we are going to discuss in this three-dimensional figure is it is sphere or hemisphere. We will also see some of the questions on hemisphere also, which will come in the examination. Sphere or hemisphere is what we are going to discuss, and then we are going to discuss some questions based on prism, and the last thing what we are going to discuss here is on pyramid. We will also see approximately how many questions we are going to discuss in each of these concepts. Cube somewhere around close to around 30 to 35 questions. Close to 30 to 35 questions is what we are discussing in cube. Similarly, cuboid, close to around approximately 30 to 35 questions we will discuss. Cylinder we will discuss close to around 40 to 50 questions. Approximately anywhere in this range of 40 to 50 questions we will discuss in cylinder. Cone also we will be discussing approximately 40 to 50 questions. And next comes sphere or the hemisphere, close to around approximately 50 questions we will discuss here. And prism and pyramid, approximately we will discuss some 30 questions. This is our target for the next few days of our classes. We are only concentrating on this very important concept on mensuration three-dimensional figures, because this is something which ANC students were not taught earlier, and ANC students found it very difficult to learn this concept by using some traditional ways of solving. Let us simplify our problem solving to the greater extent, and let me make as much as possible from our end to make the problem solving at the most easiest way possible for our students, sir. Chalo sir, let us start immediately. This is our target for the next few days of our classes. We will see how best we can cover all these particular topics and learn the problems in the most easiest way possible. Now, we all learned two-dimensional figures these days. Now, in these two-dimensional figures, what is that we have learnt in these two-dimensional figures? We have learnt triangles, so many things, rectangles, square, so many two-dimensional figures is what we have discussed in the past. In all these two-dimensional figures, what we'll be having is, we will be having the length. We will be having the length of the dimensional figure, and we will also be having the breadth. For example, if we consider a paper, if we consider a sheet of paper will be having a length, a sheet of paper will be having a breadth. But in this three-dimensional figure, we are moving one step ahead and we are learning. In this case, we will also have the length like the two-dimensional figure. We will also have the breadth same similar like the two-dimensional figure, but in this 3D figures we will have one more extra parameter called as height, one more extra parameter called as height. That is the reason this is named as three dimensionals. There are three dimensions for a particular figure. One of the dimension is length, second dimension is breadth, and the last dimension is what we call as height, which was not actually present in a two-dimensional figure. Now before moving on to more and more concepts on building this three-dimensional figure and solving the problems on three-dimensional figure, there are few things that definitely every student who is listening to the class should know. I will definitely explain you these things before moving on to our problem solving, because in our problem solving these things might be very handy and effective. So before solving our problems or learning the concept, we will see all these things and then we will move forward. Sir, what is that you want us to know? What is that you have written the heading called as things to know? What is that we need to know in this particular case? Very simple, sir. These are some of the people who already know it. Suppose if the given unit is in inch, and if I want to express this in terms of centimeter, 1 inch is nothing but 2.54 centimeter. These are all some values which will be very handy while solving our problem. So that is the reason I am discussing right now itself. 1 inch is nothing but 2.54 centimeter. Similarly, if I want to say 1 meter, if I want to convert it to inch, 1 meter will be equal to 39.37 inches. 1 meter is nothing but 39.37 inches. Now, if I want to find what is 1 foot in terms of inches, if we are having the foot value as 1, then it is called as 1 foot. If the value is not 1, then it becomes a plural word called as feet. Feet is nothing but the plural of a foot, right? I hope everyone knows this. 1 foot, if I want to convert it to inches, this will be 12 inches, right? This will be 12 inches. These are three values that you need to take care of it. Similarly, if I want to continue further, now this is something which I wrote it just a couple of probably 1 minute before. 1 meter is equal to 39.37 inches, and I also wrote as 1 foot is equal to 12 inches. Now what I will do is I will just expand this 1 meter. Instead of directly writing it in terms of inches, I will write it as 39.37. I will write it as 36 inches. I will write it as 36 inches plus 3.37 inches, because 36 inches plus 3.37 inches is nothing but 39.37 inches itself. But I also know that every 12 inch is considered as 1 foot. For 12 inch we consider it as 1 foot. For 36 inches we consider it as 3 feet. So this can also be written as 3 feet plus 3.37 inches. That means instead of directly saying 1 meter as 39.37 inches, I can also say it as 1 meter is equal to 3 feet plus 3.37 inches, right? 3 feet plus 3.37 inches. These are some of the things that you need to know before moving on. Now there are few more extra things that I definitely want you people to know it. Then we will move on to the concept of cone, cube, cuboid, or whatever it is, sir. First let us see all these things and then let us take it forward. Now see here, these are some of the terminologies you should be very familiar with. One is kilo, next is hectare, and then comes the deca. Suppose if I keep this as my base value, that is meter, I will keep it as my base value, and then follows deci, and then follows centi, and then follows milli. What is the meaning of all these things? You know all these things, but I am making it even more easy for you people. Now I will take this as my base value. the base value whatever I am taking is meter or liter, right? The unit can also be in terms of liter also sometimes. Meter or liter, I will call it as 1, right? I will consider it as 1 meter or 1 liter. Now if I want decameter, if I want hectameter, if I want kilometer, I am moving forward right now, or I am moving upward right now. I am moving upward means this 1 should become 10. So decameter is nothing but 10. Hectameter is nothing but put another 0, it is 100. Kilometer is nothing but put another 0, it is 1000. That is moving upward. Similarly, if I want to come downward, I will keep my base value as 1 once again. So this is deci. Deci, if I want to write in terms of 1, it is 0.1, or I can also write it as 1 by 10, right? I will write it as 1 by 10. Similarly, centi is nothing but it is 1 by 100. Milli is nothing but it is 1 by 1000. That means again I am saying you, sir, I am keeping the base value as meter or liter. Depending on the unit given in the question, you can change it accordingly. That I will call it as 1. If I want to move upward, 1 meter is nothing but, or if I want to move upward in a simple language, deca is nothing but 10, putting 1 extra 0 after 1. Hecta is nothing but 100, putting 2 extra zeros after 1. Kilo is nothing but 1000, putting 3 extra zeros after 1. Similarly, if I want to move downward, so 1 is considered as the base value. Deci is nothing but 1 by 10. Centi is nothing but 1 by 100. Milli is nothing but 1 by 1000. Now, you might ask me a question, sir, can you explain with some example? Now, suppose for example, I am asking you, suppose I want to convert 1 kilometer. I want to convert 1 kilometer into meters. 1 kilometer is equal to how many meters? It is very, very simple, sir. 1 kilometer is equal to how many meters is what I require. First one example I will explain you very easily, or in a very detailed manner. Then you need not do all those things. In fact, 1 kilometer is equal to how many meters? These two are the parameters they are asking. Now cross multiply. If I cross multiply, this 1 will go to the left hand side and it becomes 1 into kilo. So this is nothing but 1 kilo. Right hand side it is 1000 into meter. It becomes 1000 meters. So 1 kilometer is nothing but basically how much? It is nothing but 1000 meters. Or instead of doing all these things, 1 kilometer is equal to how many meters they are asking. 1 is becoming 1000. Multiplying factor is how much? Multiplying factor is 1000. Answer for this question is 1000. Suppose one more example. I want to convert, suppose I want to convert hectameter into decameter. 1 hectameter is equal to how much decameter? This is my simple question for my students. 1 hectameter is equal to how much decameter? Now take those two parameters and then simplify. Very simple. 1 hectameter is equal to how much decameter? That means decameter is represented as 10. Hectameter is represented here as 100. 10 is becoming 100. Multiply by which value? Multiply by 10, because 10 into 10 is only 100. So in simple language, 1 hectameter is equal to how much? 10 decameter. One more question before I proceed further. Suppose if I want to ask you, 1 meter is equal to how many millimeter? Let us come below right now. The first two examples we moved upward. Now let us come downward. 1 meter is equal to how many millimeter? Now same logic. 1 meter is what they are asking. How many millimeter is what they are asking. Meter is represented by 1. Millimeter is represented by 1 by 1000. So 1 is becoming 1 by 1000. 1 is becoming 1 by 1000. So it should be multiplied by 1 by 1000. That is what you will do it. But that is when I am moving upward, sir. So when I am moving upward, whatever you are saying is right. Now it is the reverse case. Now it is the reverse case. Very simple. 1 by 1000 should become 1. 1 by 1000 should become 1. Multiply by which value? 1 by 1000 into 1000 is nothing but 1. That means 1 meter is nothing but equal to how much? 1000 milliliter. I hope it is clear for you. One last example in this case before we move forward. Suppose if I want to convert 1 decameter into decimeter, what is the value of 1 decameter in terms of decimeter? Same logic I would like to implement here also. 1 decameter, that means decameter is nothing but here it is represented as 10. Decimeter is here, it is represented as 1 by 10. Now same logic, 1 by 10 should become 10. 1 by 10 should become 10. Multiply by which value? Multiply by 100, because 1 by 10 into 100 is nothing but 10. 1 by 10 into 100 is how much, sir? It is 10 only, right? So that is nothing but this value. 1 decameter is nothing but how much? It is nothing but 100 decimeter. You might get a doubt. Why are we discussing all these things? You will come to know as I proceed with my upcoming classes. These are all some of the values which will keep coming in our problem, probably in future problems. So I don't want you people to get confused at that point of a time. So it is my responsibility to teach you these things right now itself, so that it should not be a confusion for you in the future. I hope till now whatever we have discussed, till now we have told that what is the class, what are the topic that we are going to cover in mensuration three dimensional, along with how many problems approximately in each topic, and then a very small explanation about two dimensional and three dimensional. What is the small minor or major, whatever you can call it, difference between 2D and 3D, and then I have told you how or probably what are the things that you need to know before we move on to problems. What is inch into centimeter, meter into inches, foot into inches, all those things we have seen. And then this comes the very crucial conversions, meter to kilometer, meter to decameter, decameter to decimeter, decimeter to millimeter. Like that you can do any conversions if you know this particular screen, whatever I have written right now. That means in simple language, I took the base as meter or liter and I called it as 1. Moving above it is putting one extra zeros, and moving below it is nothing but dividing by 10, 100, 1000, etc. I hope till this point it is very clear for every student who is listening to the class. Now before I move forward, before I move on to the next few varieties of problems, we discussed this already. Two-dimensional figure is nothing but length and breadth. The figure, whatever the geometrical figure that will be given, you need to find the length and the breadth, or the length and the breadth are the two dimensions of that particular geometrical figure. Or in simple language, in two-dimensional figure, we find perimeter of that two-dimensional figure, and we also find area of that two-dimensional figure, right? In two-dimensional figure we find the perimeter and we also find the area. In three-dimensional figure we find the area in this case also, but what we generally call it as, that area we generally call it as the surface area. And because there are three dimensions, one is the length to breadth and the other is the breadth to height, and then because there are three dimensions for this geometrical figure, we also will be interested in finding the volume of that three-dimensional figure. That means the two parameters that we are mainly concentrating in three-dimensional geometrical figures are, one is to find the surface area and the other is to find the volume. Like the way we concentrated more on finding the perimeter and the area in two-dimensional figure, in three-dimensional figures we will be concentrating more on finding the surface area and volume of those geometrical figures. Now let us start analyzing and understanding what is the meaning of all these things. First of all, I wrote something called as the surface area. What is the meaning of this surface area? Unfortunately, I will not be visible when I am taking this class. So geometrical three-dimensional figures probably is all about visualization. It is all about how you visualize the things of that particular geometrical figure, so that you will understand it much more effectively if your visualization is very strong. I could have showed you some of the actual geometrical figures, probably a book or a cube or something like that, if I am visible in this particular video, but unfortunately only audio will be audible for you people, but I am not visible live. So it is about my students visualization that make this topic more important and more easy for you people. Have that visualizing things, I will try my level best for you people to making you people understand what is that I am speaking, but I think that you are very convenient in visualizing also. Now see here sir, let us immediately jump onto it. Now first thing what we are going to discuss here is surface area. Now first of all, in this surface area, basically in this surface area also can be further classified. One is called as the flat surface, one is called as the flat surface. Suppose for example, flat surface is nothing but, I can take an example of a mobile screen. You all have mobile. That mobile screen is what I call it as flat. It is not something a round or some other shape, geometrical shape. It's a flat surface what we have mobile screen. Most majority of the mobile screen is what I am talking about. This is what we call it as lateral surface area, right? This is what we call it as lateral surface area. Lateral is nothing but flat, right? Lateral is nothing but flat. And we have another kind of surface area. Suppose just visualize by taking a water bottle for example. Suppose assume that I have a water bottle in my hand. Now there are so many different shapes of water bottles that are available, but I am talking about a general kind of water bottle where it will be little curved surface. So the second kind of surface area what we have is a curved surface area, right? The second kind of surface area what I am talking about right now is a curved surface area, wherein one simple example for it is a water bottle which is having a curved surface. Yes, I do agree that the water bottles are having so many shapes right now in the present world, but I am talking about a generic case where the water bottle is curved. So there are two types of surface areas. One is the lateral surface area, where it is also called as a flat surface area, where I gave a small example of a mobile screen for your better explanation or understanding, and the other one is a curved surface, which is a water bottle where it will be curved in shape. Now you might get a doubt, what is the meaning of this lateral surface area? Yes, I told an example, mobile screen, which is a flat kind of a thing, is what I said, but I want you people to dig in little more deeper and understand the inner meaning of this lateral surface area. Now what is this lateral surface area? Very simple. It is very simple. You take any three-dimensional figure. Listen to my statement very carefully. You take any three-dimensional figure. Suppose you take a book, right? You take a book. If you remove the top and bottom surfaces, that means if you want, you can take it out. So right now when I am speaking itself, just take any book of your choice, any book. It will be having 6 surfaces totally. The top surface, which is nothing but your binding, the bottom surface, which is also nothing but your binding, and there will be 4 different sides, corners, different 4 other surfaces. So you can visualize it by taking a book right away. Suppose if you take a book which is also a 3-dimensional figure, if you remove the top surface and the bottom surface and consider the other 4 surfaces, if you remove the top surface and the bottom surface and remaining 4 other surfaces are present, if you remove bottom and top, if you consider those other 4 surfaces, then it is becoming a lateral surface area. So I am repeating once again, lateral surface area is nothing but removing the top surface and the bottom surface. Removing the top surface and the bottom surface and considering the other 4 surfaces. that we usually call it as the lateral surface area or the flat surface area. Now, similarly, if you take a water bottle, I told you that the water bottle will be curved in shape. Majority of the water bottles is what I am talking about again. The water bottle will be curved in shape. So this water bottle, if you consider and if you remove the top and the bottom, and if you remove the top and the bottom surfaces and consider only the curved portion, that means you can visualize right now by taking a water bottle, the top portion which is not too much curved and the bottom portion which is not curved again. If you do not consider it and if you consider only the curved surface, only the curved surface where it is round, then that is called as curved surface area. I hope you got a little idea of what I am trying to speak. It would have been much more easier for me to visualize or probably show you the things and explain you if I am live or probably if I am visible in this video, but unfortunately because of only audio being audible for you people, I am trying my level best to make you realize how it is, however it is possible from my end. So this is what we call it as lateral surface area and the curved surface area. That means these are some things with respect to two kinds of surfaces. One is the flat one and the other is the round one or the curved one. Now there is something also which we will usually take into account when we are solving problems in three-dimensional figures. That is called as total surface area. Let me write the heading here. That is called as total surface area. Now the name itself suggests total surface area means it is the total is nothing but the entire thing should be taken into account. That means total surface area is nothing but, if I am taking a curved surface, then it becomes a curved surface area, or if I am taking a flat surface, then it becomes a lateral surface area. So depending on the geometrical figure which you have taken, either it is curved surface area should be taken or it is lateral surface area that should be taken, and this will be summed up with, this will be added with the area of the bases. That means earlier I told remove the bases and then take only the four surfaces in terms of a book, or only the curved surface in terms of a water bottle. Now don't remove anything. Total surface area is nothing but, the name itself suggests it is total. Total means everything should be taken into account. I don't want to remove anything in this case. So total surface area is lateral surface area plus the area of the bases, or it is curved surface area plus the area of the bases. This is something which you need to know. Now I already told you before taking all these things, in three-dimensional figures there are two main important things that we will learn. One is the surface area. A small introduction about the surface area is what I gave you right now. We will see in depth about the surface area as we proceed with our problem. Nothing to worry about that part. And another thing is what is called as volume. What is this volume also? We will see what is the meaning of volume, everything, when we take more and more problems. But for the time being, a very important explanation, just a one-liner explanation for the time being. Suppose for example this is the water bottle. Suppose for example this is the water bottle which is having some water, right? The diagram is not that proper. So this is the water bottle which is having some water. Now this water bottle is present with some axis, x-axis and y-axis, some coordinates will be there. Now I will shift this water bottle from here to here. I will shift this water bottle from here to this position what I am drawing right now. Now if I shift this water bottle from one place to another place, will the volume of that water bottle change? That means volume is nothing but length into breadth into height. We will see all these things in the further classes, nothing to worry. Volume is nothing but LBH for a three-dimensional figure. All the three need to be considered. So if I just shift the position from this place, from this place to this place, will the volume change? Definitely the length, breadth, height will not change. Or instead of having the water bottle in this shape, I will just rotate that water bottle. That means I will reverse it. I will just reverse it like this. If I reverse the water bottle, will the volume of the water bottle change? Volume is basically length, breadth and height. No, the volume will not change once again. That means very important point for time being. For time being, let us not too much worry in detail about volume at the present situation. But one thing that is definitely for sure is volume of a three-dimensional figure. It remains same always. It will remain same. The volume of a three-dimensional figure will not change. That means even if I shift the position from one place to another place, or if I rotate, even after rotation, even after shifting the position, the volume of a three-dimensional figure will not change. That is the meaning of volume is constant, or volume is not changing. I hope the idea is very clear. Again I am saying, sir, two important parameters what we need to take into account when we are discussing about three-dimensional figure is, one is the surface area. We saw what is the meaning of lateral surface area, curved surface area and total surface area. And for small time being explanation, I told you that the volume of a three-dimensional figure, even after rotation, even after shifting, it will not change. I hope till this point every viewer who is watching this video is very clear till this point of a time. Now let us move on to individual three-dimensional figures, and we will see what are the properties of them, how we can solve some excellent problems which can be asked in the examination with respect to those three-dimensional figures. Everything we will see in detail right now, sir. Now see here. First important thing what I want to discuss is a cube. First important thing is a cube. Now, whenever we hear about this terminology called as a cube, the first thing that will come to our mind is a Rubik cube, right? The first thing that will come to our mind is a Rubik cube. Whenever I am explaining a problem on Rubik cube, or probably a problem on cube, or probably an explanation on cube, if you have Rubik cube with you right now, or probably in your home, you can just take it and visualize whatever I am trying to say, so that your learning becomes effective. Now see here, sir, before learning more in detail about cube, I want to explain first about cuboid. First I want you people to know about cuboid, then let us come to cube. Now see here, suppose for example, let me draw it. My diagram is not that great, so please consider whatever I am trying to draw. So you will understand how easily you can draw the diagram also after some time, nothing to worry. But for time being, I am just drawing it like this. Now first let us understand cuboid, and then we will see the remaining parts. Now see here, this cuboid, I told you that in a three-dimensional figure, you will be always having a length, you will always be having breadth, or we call it as width, and you will also have something called as height. Now, this is something what I was referring to as length. This is nothing but a length. Similarly, this particular portion is nothing but the width. And what is the other thing which I told you? Height. This is something which I was referring to as height. Any three-dimensional geometrical figure will have these three dimensions called as length, breadth and height. Length, breadth and height is something which is having in a three-dimensional figure. Now see here, what I told you is, we will first see what is the meaning of cuboid before we moving on to cube. Cuboid is nothing but it is a rectangular box. It is a box basically. It's a very simple explanation what I am giving you right now. It's a box basically which is similar to a rectangle, wherein the length, the width and the height all are different. cuboid is a rectangular box which is having the three dimensions such as length, breadth or the width and the height. Length, width and height of a three-dimensional figure. If they are different and if it is similar to a rectangular box, then we call that rectangular box or a three-dimensional figure as a cuboid. Now you might get a doubt. Now if they are different, we call it as cuboid. What if length, width and height, all the three dimensions or all the three parameters are same? If all the three parameters for a rectangular box are same, then that is something is what we call it as a cube. I hope you are clear with the logic. There is no as such difference between cube and cuboid, except the only small difference as a cuboid is a rectangular box where length, width and height are different, whereas a cube is also a rectangular box. If I make all these three dimensions length, width and height as same, then we call it as cube. Let me draw it for your explanation purpose. Again and again I am saying you, my diagram is not drawn to the scale. I am not that great person who can draw the diagrams, so please consider the diagrams what I am drawing, sir. Give me a time so that let me draw the diagram at least a little neatly, if not too rubbish. Now this is definitely not a cube, but please consider it as a cube for time being. Now see here, what I was referring to is, let me show it to you people. Now this particular length, if I call it as a small letter a for example, this particular width, if that is also equal to a, and this particular height, if this height also is equal to a, then we call this three-dimensional figure as a cube. I hope you understood the difference between a cube and a cuboid. Now the cube and a cuboid, you understood that they both are almost similar with a very small difference. Now this cube and a cuboid, they will be having 6 faces. Now let us come to each and every in-depth meaning or analysis of these geometrical figures. In both cube and cuboid, there will be 6 faces totally. Now what do you mean by faces? Faces means, suppose you take a book. I told you sometime before itself. You take a book right now. The top binding is one face. The bottom binding is another face. And there will be 4 other faces which are smaller. It will not be that compared to top and bottom, but the other 4 faces are smaller faces. But totally there will be 6 faces for sure. In a cube or in a cuboid, totally there will be 6 faces. There is no doubt about it. There will be 6 faces in both cube and a cuboid. Similarly, there will be total of how many vertices in cube and a cuboid? Let us count it right now. This is one of the vertices. This is my second vertices. This is my third vertex. When I am talking about individual things, I call it as vertex. This will become my fourth vertex. This is my fifth vertex. And here comes the sixth vertex right now. And this will be my seventh vertex. This will be the seventh vertex. And this will be the eighth vertex. That means totally there will be 8 vertices in a cube and a cuboid. Sir, there is no difference between cube and a cuboid, except that in a cube all the 3 dimensions are equal. In a cuboid all the 3 dimensions are unequal. That's the only difference. That does not mean that the number of faces will change, the number of vertices will change, the number of edges will change. No, it will not. All the other parameters or the properties remain the same. That means there will be total of how many edges? There will be total of how many edges in a cube or a cuboid? There will be a total of 12 edges in a cube or a cuboid. Let me show it to you people. At least a few of them. Let me show it to you people. Now this is one of the edge. This is one of the edge. This is one of the edge. This is the another edge. Like that. This is the another edge. This will be the fourth edge. This will be the fifth one. this is the sixth one, this is the seventh one. Like that, if I count it, totally there will be 12 edges in a cube or a cuboid. That means in the base, this is what I am calling it as base right now, sir. I am drawing it here for you people. So this is okay. 1 minute. Let me use a different color so that you will also realize what I am trying to say. This is what I am calling it as a base. The green color highlighted portion. The green color highlighted portion is what I am calling it as a base right now. That means in base there will be 4 edges. Similarly, in the top, the top green color portion is what I am putting right now. In the top there will be 4 edges. In base 4 edges will be there, top 4 edges will be there, and toward the other sides there will be another 4 edges. Total of 12 edges will be there in a cube or a cuboid. So again I am repeating one more time, sir. There will be totally 6 faces, 8 vertices and 12 edges in a cube or a cuboid. So based on these properties of a cube or a cuboid, a great mathematician, you all definitely will be knowing his name. A great mathematician, Euler. Euler proposed a formula. Something what we call it as Euler's formula based on these values, and he proposed that for any polyhedron, you take any polyhedron of your choice. The next question comes to your mind is, what is a polyhedron? Very simple, sir. Polyhedron is also a 3-dimensional figure where every surface is a flat surface. I already told you what is the meaning of a flat surface. If every surface is a flat surface, then that 3-dimensional figure is a polyhedron. So Euler proposed that for any polyhedron, if I call the vertices as V, if I call the faces as F, if I call the edges as E, then he told that vertices plus faces minus edges will always be equal to 2. Very important notation, extremely important. This notation or this Euler's formula was also asked in CHSL paper 1, sir, right? Very important. Euler proposed that for any polyhedron, it is always true that V plus F minus E is equal to 2, where V is nothing but the number of vertices, F is nothing but number of faces, and E is nothing but the number of edges. I hope the idea is very clear for you people till here. I hope the idea is very clear for you people till here, sir. Again, I am just revising. We started with the cube, but before we started moving on to deeper into cube, in fact, after I explain once again, I am just going in depth about the cube in the next few minutes. We learnt what is cuboid. Cuboid is a geometrical figure, 3-dimensional geometrical figure where length, width and height are all different. If all these 3 dimensions, length, width and height becomes the same, then it is termed as a cube. In a cube, there will be total of 6 faces, 8 vertices and 12 edges. And based on these parameters, it is not only for a cube or a cuboid. Euler proposed it for any polyhedron, saying that V plus F minus 2 minus E will always be equal to 2. And I already also told that this was also asked in CHSL paper. I hope till here it is very clear for you, sir. Now let us go little more deeper into cube. We did not discuss so many things in cube as of now. Now let us go little deeper. Let us see what are the things we can learn from this. Now see here, sir. Let me draw the diagram once again, because I cannot keep on revisiting to the previous slide. So better is to draw it once again. Again and again I am saying, I am not a good person who will draw the diagrams neatly in a good way. Please consider this as a cube, where the length of this cube is A, width of this cube is also A, height of this cube is once again considered as A. Right? Now see here, sir. Now suppose for example, I want to find the lateral surface area of this cube. I already told you the meaning of lateral surface area. Now in simple language, lateral surface area of cube is what I need to find, or we also call this as area of four walls of a cube. Area of four walls of a cube. What is the lateral surface area? Why? Sir, why are you saying it as area of four walls? Now, I already told you, sir, lateral surface area means for any three-dimensional figure, remove the top surface and the bottom surface, consider the other surfaces, then it is called as lateral surface area. Now in this particular cube, in a cube, how many, what do you say, like how many faces will be there in a cube? Totally there will be 6 faces in a cube, which we already discussed. 6 faces. Out of those 6 faces, I will remove the top face, I will remove the bottom face, I will be left with another 4 faces. That is what I wrote here as lateral surface area of cube is also called as area of the 4 walls. Remaining 4 walls, if I take the area, it becomes the lateral surface area. Now let us move it. Let us move forward, sir. Now see here. I want to find the lateral surface. Now can I say that in this particular cube, whatever I have written, in this particular cube, whatever I have written, you can definitely take, first of all, in a cube there are 6 faces, you know it. In a cube there are 6 faces. Each face, if you see here, if you observe carefully, each face is a square of side A. That means this is one of the face. Agreed, sir? This is one of the face out of the total 6 faces. The black highlighted color is nothing but one of the face of a cube, and that is nothing but a square. What is the side of the square? Side of the square is A. You can see it here also, right? The side of the square is A. This also is nothing but A only. That means it's a square. Length and breadth are equal. The side of this square is A. This is not only true for one face, this is true for all the 6 faces. That means, can I say that area of one face is A square, because area of a square is nothing but area of this face. Area of one face is nothing but length into breadth. It is nothing but A square. But I definitely want to find the lateral surface area of this entire cube. Lateral surface area is nothing but area of 4 faces. For one face it is A square. For 4 faces it is 4A square. Very simple, sir. Therefore I can conclude that lateral surface area of a cube, lateral surface area of a cube is nothing but 4A square, where small letter A represents the side of a cube. I hope you are very clear with how to find the lateral surface area of a cube. Now see, sir, you might by heart this value. You might by heart from your textbook saying that lateral surface area of a cube is 4A square, total surface area will be 6A square. All those things you can by heart it. But I don't want you to by heart it. I want you to understand the concept. Now if the lateral surface area of a cube is 4A square, what should be the total surface area of a cube? Very simple. Totally how many faces are there for a cube? Totally, including the top and the bottom faces, there are 6 faces. Totally it is 6 faces, and each face is having a area of A square. I already told you here. For one face it is A square. For 6 faces it is 6A square. So lateral surface area is 4A square. Total surface area is 6A square. Now similarly, these are all something which can be very easily derived, sir. What should be the volume of a cube? I already told you. There are 2 important terminology that we need to consider in 3-dimensional. One is the surface area, and the surface area is divided into lateral and total. Similarly, there is another parameter called as volume. That is what we are learning right now. Now, first thing is, a cube is nothing but a prism, right? A cube is a prism. We will come to it when we learn lot of things about prism later on. A cube is like a prism. I am not saying that it is exactly a prism. It's like a prism. That means volume of a cube volume of a cube is length into breadth into height. Usually the volume of any geometrical figure is it is a combination of length, width and the height. All the three dimensions need to be taken care of. But for a cube, all the three dimensions are equal, and in our example it is equal to small letter a, so it is a into a into a. So volume of a cube is nothing but a cube, where a is the length or the width or the height of a cube. I hope you are clear till this point of a time. These are all some things which I will definitely use it in my problems, but I don't want you people to keep on deriving in the problems when solving the problems. You should be very fast enough in solving that particular problem. That is the reason I am explaining in depth. I am teaching you how to derive all these things also in right now today's class itself, so that you will not struggle while solving the problems. I always believe conceptual clarity should be so strong, so that problem solving will never be a difficulty, sir. I am a firm believer of it. Now, these are the terminologies what we saw right now. Now, there is another thing that probably which might be asked in the exam. Whatever might be asked in the exam, let us try to see all those possible angles. Diagonal of a cube, right? The diagonal of a cube is what I need to consider, or what I need to find. Now, before finding the diagonal, let me draw the cube once again. Diagram not drawn to the scale one more time. My sincere apologies for that. Now, this is a cube. Please consider this as a cube, sir. Now, please consider this as a cube. Now, see here, sir. I want to find the diagonal of this cube. Now, what is the meaning of diagonal? Now, this is one of the vertex of the cube. Similarly, this is another vertex of the cube. If I call this vertex as A, if I call this vertex as B, diagonal of a cube is nothing but the maximum length or the maximum rod that can be placed in a cube is nothing but the diagonal of the cube. I am repeating once again. I have a cube with me right now. I want to place a rod inside that cube. I can place so many small rods inside that cube. But I don't want to keep those small rods and make it as very huge number of rods inside that cube. I want to keep one rod such that that rod should cover the maximum distance or the maximum length. I am repeating, sir, the maximum length that can be placed in a cube is nothing but the diagonal of the cube, or in other language, the maximum rod that can be placed in the cube is nothing but the diagonal of the cube. In my example, the rod which I was referring to is AB. AB is the rod which I am referring to, and AB is the diagonal. So, in simple language, the maximum distance between the 2 points in a cube is the diagonal of the cube. You might ask me a question, sir, if I name this point as point C, these are also two different points in a cube. Will this not become diagonal? It will not become diagonal because that is not the maximum distance. So, diagonal AB is maximum compared to AC. AC will be definitely lesser than AB for any cube. So, the diagonal is always the maximum distance between any 2 points in a particular cube. I hope the idea is clear. Now, the next question arises is, what is the diagonal of the cube? What should be the diagonal of the cube? Diagonal of the cube is nothing but a root 3, where a is nothing but the length or the width or the height of that particular cube. Now, again the next question that will arise for sure is, how are you sure that the diagonal of the cube is a root 3? Listen to this carefully. That means indirectly you are asking me, what is the proof that the diagonal of the cube is a root 3? Let us also derive it, sir. Let us not be that lazy. Let us also derive it. Now, this AC, I will call it as small letter A. this value width is also small letter a. Similarly, this height also I will name it as small letter a. Now this point I will call it as point D, right? This point I will call it as point D. Now, because this AC is A, definitely BD also will be A. Now, if you consider, if you see the cube, you will understand in a much more better way. This angle D will be forming 90 degrees. This angle D will definitely form 90 degrees. That means this AD is nothing but the diagonal of that particular geometrical figure. AD is nothing but the diagonal of that geometrical figure. Now this value is A. That means AC is A. CD is also A. According to Pythagoras theorem. According to the Pythagoras theorem, let me call this point also as E, sir, so that you will not have confusion. That means, can I say that ACDE, ACDE, it is a square. Definitely it is a square of side A. It is definitely a square of side A. And angle D is 90 degrees because it is a square. All the angles are 90 degrees. Angle D is 90 degrees. If I draw a line from A to D, AD is the diagonal of this particular square ACDE, right? AD is the diagonal, and because angle D is 90 degrees, and this BD is equal to A, I can say that this angle, this triangle ADB, the triangle ADB, it is nothing but a right angled triangle. I hope you are understanding, sir. This is 90 degrees. And this angle, this triangle ADB is what I am speaking about. It is nothing but a right angle triangle, and this is side A. This also is side A. So the diagonal of the bottom square AD will be A root 2. Sir, how it is A root 2? Let us not go into diagonal of square right now, because we are interested in finding the value for diagonal of cube. It is A root 2. Now can I say that this becomes a Pythagoras theorem right angled triangle. Triangle ADB, the right angled triangle. In that AB is the hypotenuse. So AB square is equal to AD square plus BD square. So this becomes the Pythagoras theorem. AB's hypotenuse square is equal to sum of the squares of the other two sides. AD is nothing but the diagonal of the square. The value is A root 2. So this is A root 2 whole square plus BD value is nothing but A. It is A square. So this is A root 2 whole square is 2A square plus A square. So AB square is nothing but 3A square. But I don't want AB square. I want the value of AB. And AB is nothing but the diagonal of cube. AB value is square root of 3A square. It is nothing but A root 3. And that is the reason diagonal of a cube is nothing but A root 3. I hope the idea is very clear for you people. Again I am saying, sir, I am still in the first geometrical figure. I started with the cube, and I told that instead of learning cube directly, let us understand what is cuboid initially. Cuboid is length, width and height are different. If I make all the length, width and height as same, then the same geometrical figure of cuboid will turn into a cube eventually. And in a cube, there will be 6 faces, 8 vertices and 12 edges totally. And Euler proposed that for any polyhedron, V plus F minus E will always be equal to 2, where V, F and E are nothing but vertices, faces and edges of a polyhedron. And then we moved on to little bit deeper into cube, and we start what is the surface area of cube. Lateral surface area of cube is 4A square, because cube is nothing but eventually it is nothing but a combination of so many squares. For each square, the surface area or the area of the square is A square in this case. For one square it is A square. So Lateral surface area means totally out of 6 faces, we should remove off 2 faces, top and bottom. So 4 are left out. For 1 square it is a square. For 4 squares it is 4a square. So LSA is 4a square. Similarly, total surface area is 6a square. If I want to find the volume of a cube, volume is nothing but length into breadth into height. All the 3 dimensions should be considered in a 3-dimensional figure for a volume case. But for a cube, all the length, width and height are equal. So it is a into a into a, which is a cube. And one more parameter that might be coming in the examination with respect to cube is diagonal. The diagonal of a cube is a root 3, and that is something which we have derived also, and finally eventually got the value as a root 3. So this is what we have learnt so far with one of the geometrical figure called as cube, and a little extension of it is called as cuboid. We will see more and more of things about cube and cuboid or whatever it is in our upcoming classes, and learn a lot of problems in solving in the most easiest way possible. I hope till this point of a time it is very clear for you people, sir.